In this lesson, we'll talk about what a software-defined network is, what the advantages of an SDN are over conventional network architectures, and I'll give a brief overview of different parts of the course. We'll talk about history, where SDN came from, infrastructure, in particular how SDNs are designed and built, and applications, in particular what they can be used for. So first of all, what is a software-defined network? Fundamentally, a software-defined network is a type of network architecture that separates the network data plane, that is the network devices that forward traffic, from the control plane, that is the software logic that controls ultimately how traffic is forwarded through the network. The separation of the network's data plane and control plane allows a network operator to control network behavior from a single high-level control program. There are typically two parts to SDN infrastructure: the data plane, that is programmable switches, and the control plane, that is the controllers and the applications that control how the data plane forwards traffic. Deployments of software-defined networking are often used to solve a variety of network management problems in real networks, and we'll talk about a lot of examples throughout the course. To understand software-defined networking, it sort of helps to compare the software-defined networking paradigm to the current conventional network architecture. So the picture below shows an example of the current network architecture where network devices, in particular routers, are bundled with a specialized control plane and various features. So for example, if you bought a router, you'd buy the hardware for that router, but you'd also get stuck with whatever software and features were shipping with that particular router. So this vertical integration essentially binds you to whatever software and features are shipped with that particular device. This bundling effectively slows innovation. Software-defined networking effectively breaks these pieces apart. So at the lowest level, we have the data plane, or the switches, that are responsible for doing nothing more than just forwarding traffic. On top of that, we have more complicated control programs, or control plane, that speaks to the data plane through a well-defined software interface, such as OpenFlow. On top of that control plane, we might have more complicated applications written in higher-level languages that perform management operations such as traffic load balance or security types of applications. So where did SDN come from? Fundamentally, it was motivated by the observation that distributed network configuration, that is a network where all the network devices are configured independently in a low-level device-specific manner, can be very buggy and unpredictable. We did a lot of work about 10 years ago trying to build tools to cope with that unpredictability and bugginess. So what we would do is take configuration and analyze it and try to infer the behavior of the network from those lower level configuration files. One example where we did this was to take, for example, BGP configuration, analyze it, and try to figure out what the interdomain routes would be based on that configuration. But what we ultimately discovered was that inference was difficult, and it would be easier if instead a single centralized control point could just dictate the forwarding behavior of the network. So that control point would actually know the answers to those forwarding questions already. We did this in the context of the Internet's interdomain routing protocol, the Border Gateway Protocol, or BGP, and that central control point was called the Routing Control Platform, or RCP. Later, that architecture was generalized into something called the 4D architecture. In the 4D architecture, shown below, the data plane sits at the very lowest level and is responsible for forwarding network traffic. In between, or sitting on top of the data plane, are the discovery and dissemination planes. Discovery basically allows the network control point to discover what resources are available. And dissemination basically talks about how to discover a network topology. On top of that, we have the logic that actually controls the behavior of the network, or the decision plane. So that's essentially conceptually like an RCP. A few years later, we saw another instantiation of SDN called OpenFlow, whereby an SDN or a high-level controller could control the behavior of switches through a well-defined interface. And we'll talk about the OpenFlow architecture and control channels in a lot more detail in later modules. So what are the advantages of software-defined networking over conventional network architectures? Well, first of all, SDNs are much easier to coordinate. In particular, a network operator can write a program that allows the behavior of different network devices to be coordinated. So for example, if you wanted to load balance traffic across a network, or if you wanted to make sure that your security policies didn't interfere with your load balance policies, these types of coordination are much easier in a software-defined network than they would be in a conventional network where the network operator has to configure and control each device independently in a low-level vendor-specific language. They're much easier to evolve. So if you go back to that picture where we talked about vertical integration, it's very tough to evolve because the software is bundled with the hardware and whatever features are also bundled with that. If we break that apart, as we did with SDN, well, you can evolve the control plane or the software that controls the network behavior much more easily because you've decoupled that from the underlying network devices. If you're controlling the behavior of a network from a high-level program, this potentially makes the network behavior easier to reason about because you can look at a single program and figure out what that program is going to do and how it's going to control the network. And finally, it makes it easier to apply various conventional computer science approaches or things we've learned from other domains like programming languages, software engineering, and testing to some of these older network management problems that we haven't been able to apply these techniques to before because we've been operating at such a low level. So SDN infrastructure has two parts. The first is the control plane. That's the network's brain. Right? That's essentially what is controlling the behavior of the network. The control plane can be run separately from the underlying network devices, the routers and switches that actually do the forwarding of the traffic. The control plane also computes the logic of how traffic is going to be forwarded through the network according to higher level policies. The second part of the infrastructure is the data plane. This is typically programmable hardware that's controlled by the control plane. There are various domains in which SDN applications can make network management easier, such as data centers, wide area backbone networks, enterprise networks, internet exchange points or interdomain routing, and home networks. So later modules in the course are going to explore how SDN can solve network management problems in a variety of areas such as these.